because they might get. Okay. So we can start with the second lecture of Professor Schweigert.
Okay, welcome back. So let me briefly recall what was the last thing we did last time. We had some notion of a vertex algebra. Think about it in a simplified way as some commutative algebra. Then we had modules over them. We had some notion, this is a tensor product over the field, as you know it from linear algebra lectures. We had some notion of bilinear operators, and we were postulating that there is a universal bilinear operator, and actually this can be shown for classes of models, which goes to, and this guy here, this is a new representation of the vertex algebra in such a way that any bilinear operator factorizes via a morphism of modules via some intertwiner. Now, the thing I have to tell you next, that you get some feeling of the category, is you can look at the expression that I've written down here on the left-hand side. It looks like a complicated expression, but let's look at the essence. So we have two modules, and then you see that here I'm taking a coordinate and I'm mapping it to minus z. And in order to come back to the original situation, I'm just shifting it back. So this is an exchange of 2 points. If I did an exchange of 2 points, I made a movement like this, because if you want to define what multiplication by minus 1 is, in a situation where you have to take fractional powers, you have to be careful how to define it. You could equally well take another move. This would give you another operation. You have to sit down and learn enough things to find out that this here is a bilinear operator. Now, if this is bilinear, it will factorize. So it will factorize, and it gives something which goes from this, and notice here I'm writing the V. So this is our fusion product of VOA modules. This is a VOA module, and it will give an intertwiner to another VOA module, but here the order is reversed. So this is, of course, just the beginning of a story. This is the beginning of a story that you can exchange points. Well, I could now go and explain it as follows. Exchanging points means that you start to have a path in the configuration space of undistinguishable points. Well, we know, for example, from condensed matter physics or from geometry that the fundamental group of this space is the braid group. Yeah? So what we get here is a systematic way of exchanging representations. And this is the origin on the representations of a vertex algebra of the following structure. It's the structure of a braiding. And this structure will be quite important. So let me briefly explain what it is about. So a braiding is a set of isomorphisms, so of intertwiners that are invertible, and here there's a apparent clash of notation. Here I'm working in a concrete category, and I have the tensor product of vertex algebras. So here, this here was the tensor product of vector spaces, and maybe I should have better written this here. Here on this blackboard, I'm working in some abstract tensor category or monoidal category, where this was, in our concrete example, the vertex algebra itself, and we have isomorphisms. Now, these isomorphisms have to obey a number of relations. And what are the relations they should obey? Well, if I'm given morphisms from V to V prime and W to W prime, then these two isomorphisms you can form. Well, if we have here an F and a G, then remember that we also had a tensor product of intertwiners. Then we can here put C W prime v prime w prime to w prime v prime, then this here should commute. And so it should be a natural transformation, technically speaking. And now we do the same reasoning as before. For the associator, we said any rebracketing should give the same way of identifying things. Now here, before we had a rebracketing which didn't change the order. Now we change the order. There should be a compatibility. This compatibility is of course investigated, and it has the form of a hexagon diagram. And I'm not going to write it here, but I'm going to mention that this is essentially expressing that if you look at these structures in concrete representations, you get solutions of the Young-Baxter equations. Yeah, so now it's time. So, and if a category comes with such a set of isomorphisms, it's called a braided monoidal category. And what we learn is that V mod is an example of such a braided monoidal category. Now, I should give you another example of a braided monoidal category, which we were going to use a lot. Well, suppose you have any you have fixed C, just a monoidal category. And a monoidal category is, in the world of categories, what an associative algebra is. Yeah, you have a multiplication that's associative in the appropriate sense. How do you find a commutative algebra from an associative algebra? Well, you go to look at the center. Yeah, what is the center of an algebra? Well, the center of an algebra is those elements Z of A for which Z times A is A times Z for all A in A. This is something you've seen in elementary courses. Now, what is the appropriate generalization in the world of categories? This is the so-called Drinfeld center. And you might be tempted to say Z of C are those objects U in C such that U tensor X is equal to X tensor U for all X in C. Yeah, this would be literally the thing, but I told you yesterday in a category never ask two objects to be equal. It's a very bad thing, because then if you change the category to an equivalent one, you will get a different notion. So two objects are at best isomorphic. So ask for an isomorphism. But an isomorphism is an additional datum. It's a choice. Maybe it exists, maybe it doesn't exist. So really what we will have here are isomorphisms for each X. Well, this should be compatible with morphisms in X, and it should be compatible with pushing several of these X's, X1 tensor X2 on the other side. And if you want to see what compatible means, it's spelled out in the lecture notes. So this is the Drinfeld center, and this is a very characteristic phenomenon that if you go one categorical dimension higher, something which was a condition becomes structure. We have seen the same thing for associativity. So this is a way to associate to each monoidal category another monoidal category, and now we have a way to move objects to the other side. And it takes you half an hour in a lecture to sit down and to prove that this Drinfeld center is commutative in the sense that it is a braided monoidal category. Okay, so now this is an example of braided categories, and now I have to explain something again about vertex algebras. Well, there are many braidings, typically. The braiding is a structure. So this here is called a braiding, yeah? So there are many braidings, and here we've distinguished one. Now, for example, well, if you write the braiding in a diagrammatic way, then you have here M1 tensor M2 to M2 tensor M1. We are always reading diagrams from below to above. Well, in this situation, it could be that doing the braiding twice is equal to the identity. Well, you see already from the picture that this is not necessarily true. This is not a relation you have in the configuration space of indistinguishable points. And indeed, in low dimensions, we have for quasi-particles braid group statistics. So it turns out that the braiding on the category V rep is a very specific one. It has a non-degeneracy property, so it is as far away from the property that the braiding is symmetric, which would be this one. And you see, this is not a relation in the braid group. So if you have somebody with long hair around you, I'm not pointing to people in the audience, and try to implement this relation on the hair, it will have some consequence. Yeah, so this is not a relation in the braid group. And indeed, in these categories, this relation is maximally violated. Now, some of you have heard that there is something like an S matrix, and this S matrix is invertible. Actually, this is a formulation that's appropriate for a certain class of vertex algebras. There is a better formulation. Namely, our category is braided. So there is a natural functor which takes this braided category, and here I should have written V-rep, and embeds it into the center of V-rep. It does so by simply declaring the braiding which we have constructed to be the half braiding. Now, I did a choice. I said, let's take the other point in this direction. Why shouldn't I take it this one? It's equally fine. So braidings come in pairs. Yeah? And so I can use here an embedding which is induced by the braiding, and here I can equally well find an embedding which uses the inverse of the braiding. And in pictures, so here we are using the braiding, and here we are using the inverse of a braiding. Okay, so these two things combine into a single functor. So we get from V-rep and V-rep with the opposed or with the reversed braiding, we get a functor into the Drinfeld center. Well, what do I mean by this box? The box is a tensor product of categories. I'm not going to introduce the tensor product of categories, but I'm doing a cheap thing, which gives you the right feeling, I hope. If a category happens to be a mod, so modules, finite dimensional modules over a finite dimensional algebra, over a field to be in the simplest case, and you take another algebra, then, well, you know that A tensor B is another algebra in another algebra over the field. So the tensor product of categories is defined in such a way that this holds. So this is this is what I will take as the definition of the tensor product, and for those who have been exposed to more, I take the linear tensor product. Yeah, good. So what we require is that this functor, which is compatible with the braiding in a way which I'm not defining because I didn't introduce formally braided functors, but this is something you can learn easily, yeah? And this is actually an equivalence. This is the non-degeneracy of a braiding which you have on those representation categories on which the tensor product is declared, and we are using the HLZ theory. So this is remarkable. It's remarkable in two respects. The first point is, if you think about CFT, we want to go back to CFT. This here it looks like, and it is, combining left movers and right movers. So if I want to describe bulk fields, I'm combining them, but now I see I have an alternative description. An alternative description in terms of a Trinfeld center. Now you can say, okay, why is this useful? Why is the Trinfeld center useful at all? And the reason is that if you want to construct what we are going to use later, modular functors for Trinfeld centers, there are many more tools. So there are constructions like stringnet construction, state sum constructions. If your category is given in terms of Hopf algebras, there's a construction in terms of Kitaev models. So we have many more ways to deal with the data once we interpret them in terms of the Trinfeld center. What is the shortcoming of this? Well, if you go to talk to some vertex algebraists, they will typically not know the Trinfeld center. And why don't they know this? Well, because there's no intrinsic construction of this as some module, some other type of modules over the vertex algebra. This is this is very different to the situation when you're working with modules over Hopf algebra. In this case, this can be constructed in terms of Jeter-Trinfeld modules, so it has a very explicit representation theoretic construction, which is missing in the world of vertex algebras. But for us, it will be a way to deal with the combination of left movers and right movers. So this is one thing. And then the next thing is, if you work with representations of groups, then at a given moment you are using dual representations. This is unavoidable. So you take the vector space dual, and you realize, oh, there's another representation on linear forms where I'm using the inverse of a group element, or more generally an antipode. Now, here in the world of vertex algebra representations, there is a similar thing. And actually, all what I'm saying now, the hard work is again in HLZ. The categorical interpretation was part of a PhD thesis. So let's take a module, and this module should be graded, and well, if I'm saying it is graded, then I want to take in a moment of this this module, so this is graded over C. I want to take vector space duals. Taking vector space duals for infinite dimensional vector spaces is something I don't want to do. So in order to make it applicable, I should be a bit more precise and add and remark that sometimes there are additional charges around which turn this, if you take the additional gradation, into a direct sum of finite dimensional vector spaces. Yeah? Let me cheat, let me not write this, and let me assume that this is already finite dimensional. Then I can take grade-wise the dual. It's a linear algebra, and I call this M prime, but what I need to do is I have to define an action of the vertex algebra. So what I need to do is I have to define a new field map, V, Z. It's acting on a linear form on M, and this linear form, well, if this would be a group, then you would say this is the same as phi, the linear form evaluated on, and you would take the inverse of the group element, or more generally, you would take an antipode on a Hopf element in a Hopf algebra. So I have to define here something which looks like an inverse of a group element. This is the so-called opposed field map. And I'm explicit here for the following reason. Well, the opposed field map is V, Z. It is take the field map and then apply E to the ZL1. This is the Virasoro algebra. Then you take minus Z to the minus 2 and L0 and V, and you take it at the position Z1. So what is important about this formula? First, I have to change the position Z on a sphere by going to the antipodal point. And then I have to do things with the vertex, with the Virasoro generators. Now remember that on a vertex algebra, choosing the Virasoro algebra was structure. So if you choose a different Virasoro algebra from me, you will get a different opposed field map. So you will get a different notion of duality. So this notion of duality depends on the conformal structure. Depends on conformal structure on V. This is not what people in the neighboring field of quantum topology are used to. If you have a dual of a vector space, well, the dual exists or not in certain senses. Yeah? It's a property to have a dual. Here it becomes structure. So this means that really the categories we get for vertex algebras are typically not what's called rigid categories, but they have a more general duality structure. And this is uncharted terrain, which has to be worked out for CFT. And let me still tell you what the relevant mathematical structure is. So if I'm writing numbers, that's the same as in the lecture notes. Yeah, so just to orient you. So a GV category, and that's a Grothendieck, it's the same Grothendieck. Vertier category is a monoidal category together with a certain object K in C, which is called the dualizing object. The dualizing object such that, and let me simplify things a bit as compared to the lecture notes, Hom X tensor Y into K is Hom X G Y. Now here I'm shifting an element from the first entry to the second entry. So G is a contravariant functor. It changes the order of composition as a duality should be. This is something you know from first year, that if you transpose a matrix, then it reverses the order of matrix multiplication. So this is, and it's required to be an equivalence. So this is very briefly the definition of a Grothendieck-Vertier category. A Grothendieck-Vertier category is something algebraic geometers know. So if you ask an algebraic geometer, then, well, Peter was using the notion of sheaves, right? Sheaves on a variety form a monoidal category. There is a distinguished sheaf, which is the structure sheaf, that's the monoidal unit, and there's a dualizing sheaf, well, which might be constructed if the variety is not nice enough, in general as a dualizing complex. What is this guy here? It's something very natural from the VOA context. If you take V itself, then you can form V prime. And if you look at 95% of the vertex algebra literature, they will impose that V prime is isomorphic to V. But if you look at interesting examples, then you will find, for example, that the so-called W23 algebra, which is an algebra appearing in critical percolation, doesn't have this property. So no reason to assume this in general. So that's the general structure we have in a vertex algebra, and at the moment I cannot continue the theory in this generality. So now I have to make a restrictive assumption, and what I'm assuming is, well, I'm assuming a bit more than V prime is isomorphic to V. So I'm assuming that V prime is isomorphic to V. And then, well, what you can see is let's do this little exercise. It's quite instructive. If I take here y equal to, this is invertible, yeah, so if I take y equal to g to the minus 1 of y, I'm using a quasi-inverse in a naive way, then this is x, g to the minus 1 of y, this y should be an x, I have this equivalence. This here contains a distinguished element which is just the identity. It doesn't do anything. So, transporting this, I get here a distinguished morphism from X tensor, the dual, into K, and K by our assumption is equal to 1. So I'm getting something which is an evaluation. That's even true in the Grothendieck-Verdier category. What we assume on top of this is that there is also a co-evaluation. A Grothendieck-Verdier category typically does not have a co-evaluation, at least not for the tensor product we have been discussing so far. In fact, a Grothendieck-Verdier category has two tensor products, and that's why people in linear logic have been looking a lot at this type of structure, and we are just trying to learn from them. But this is a process that's irrelevant for the lecture. So here we have an evaluation. So we assume that there is an evaluation from X and X dual. Now let me introduce a notation where this goes right and I take a left dual, and this will be a morphism and into the monoidal unit, and there will be a co-evaluation which will be a morphism from 1 into X dual X, and it should obey nice relations, and these nice relations are that you can pull this diagram which contains a co-evaluation and an evaluation, you can pull it straight, and there is another diagram where you can, well, this is, I think, the same diagram. This is a bit where you can pull this straight. Yeah. So if a category has for every X such an X left dual, then C is called left rigid. Well, now you take a mirror, you look into the pictures the other way around. There is a notion that a category is right rigid, and actually now we have to go back to this Grothendieck-Verdier case. There is also a left and a right variant because I decided to push here the Y to this side. So this Grothendieck-Verdier category, the vertex algebra category, has left and right rigid, has an analog of left and right rigid, and they are actually the same. If I'm saying the same, then I mean that there is an isomorphism which identifies the left and the right dual, and this isomorphism is again nice in the sense that it is compatible with tensor products, and such a thing is called a pivotal structure. So what we learn is that representation categories of vertex algebras are braided, pivotal GV categories, and actually they are a bit more. There is a notion of a ribbon GV category, but those of you who know what a ribbon category is will understand it, and for the other ones I don't need it and I'm skipping it here, right? Okay, so these are very special categories. And one of the things that follows from identifying left duals and right duals is the following. So if I'm given a morphism from X to Y, and I'm using now the left dual, I get a morphism from Y left dual to X left dual, and I can do the same thing by turning it here to Y right dual, X right dual. These two are, well, there is a strictification result. We can assume that these two objects are actually equal. That simplifies life. And so these two things are equal. And now we get the following thing. We want to work in the end with invariant tensors. Yeah? So invariant tensors are something you know from advanced quantum mechanics, right? These are, technically speaking, in our context, an invariant tensor for the tensor product of X and Y will be some intertwiner from X tensor Y into 1. If you take threefold intertwiners, you have the usual coupling spaces you consider, which when you start to define Clebsch-Gordon coefficients. Now, here, this coupling, by the way, in the Grothendieck-Verdier context, you have to replace this by K, and you get a good theory of such coupling spaces. And maybe I should be a bit more explicit. So I could take more than one, I could take n of them, and now these coupling spaces have a very nice property. They are cyclic. They are cyclic in the sense that the following thing holds. Well, they are cyclic in the sense that if I take such a coupling, and let me draw this for x1, x2, x3, I can map this to, I take x1, I turn it around using my dualities, then I'm ending up with x2, x3, x1. Well, guess what I'm doing next? I take the x2 and I take the x3. So what I'm getting is, in the end, I will have taken all these three legs and turned them around. And here, this goes into the monoidal unit. And now, using that bending to the left and then to the right is the same as the other direction, I can undo this. So doing this n times, I'm back to exactly, here I have x1, x2, x3. This is exactly the original morphism, x1, x2, x3 into 1. So the point here is that from the symmetries of a CFT, we get a nice set of cyclically invariant tensors. Or put differently, we get a pivotal monoidal category, which we are going to use then in the skein theoretic construction. That's what I wanted to explain in this part of the lecture notes. Okay, let me just check that I explained what I wanted to explain. Yes. So now we come to the last step of preparation, and this step of preparation is I have to explain you a bit about conformal blocks. Yeah? So we will use that bulk fields in the CFT are built from combining left movers and right movers, describe them here, and use these type of constructions. We will use, but we have to relate it somehow to correlators. Now, conformal blocks for a general vertex algebra are very tricky to describe. I haven't developed the formalism. So I take a shortcut. And what I'm going to show to you is how conformal blocks look like in the specific example of theories which are built on non-abelian currents, because then I can be very explicit. Yeah? So what is the thing you want to do for conformal blocks? Well, one of the basic ideas of quantum field theory is that if you are given some representation, if you are given some vector in this representation, and if you are given a space that is nice enough that we can work with it, and in our case this should be a complex curve, so a complex one-dimensional manifold, then we should be able to form something like fields. So if you put this in at various pairwise different points, you want to get something which should be close to a correlator. Well, let's be a bit more. So we want to give sense to some expression of this type, that you have here some lambda 1, that's V1, phi lambda 1, V1 at a point P1, and so on a curve X. Well, what do we do? The following construction is natural. So I'm going to rewrite this. I'm going to rewrite this in a way which might look a bit artificial. Well, I'm going to rewrite this by saying this is a linear form. Yeah, so a linear form, beta, on what? So I take h vec lambda. This is the tensor product of all the representations. So let me call this h lambda, because this is the notation I have here in my lecture notes. We take the tensor product. This is a tensor product over C. So it's not a fusion product. And beta should be a linear form. It will depend on X, and it will depend on the points, and of course on the representation we choose. And it is a linear form in the algebraic dual. This is a huge, huge vector space. Yeah? And we want to find, well, we rewrite this in terms of xp lambda, and this should be the linear form applied to these vectors. So, in order to find such objects, I should look for such linear forms. What should these linear forms obey? Well, these linear forms should obey the symmetries that the vertex algebra encodes. So, but now the vertex algebra is, in a sense, something that's located at one point. So what I need to do is I need to find a globalized version of a vertex algebra. Such a construction exists. You can find it in Frenkel-Bensui's book, and there are more modern versions and handier versions in papers by Damiolini, which I'm referring to in the lecture notes. The construction is, unfortunately, an necessarily involved. So I'm doing here a shortcut. I'm simply assuming that my vertex algebra is generated by non-abelian currents. So we have a finite dimensional reductive Lie algebra, and simply imagine SL2. So A has 3 indices, as you know it from SL2 theory, and here we have a mode index. And yesterday I've written down that they have commutation relations which are a centrally extended loop algebra. Yeah. So in this case, it's much easier to globalize such a loop algebra to a curve. What do we take as a global version? Well, we take f of our curve x, which are holomorphic functions. Now we are using the holomorphic structure, right? Holomorphic functions on x, which have at most finite order poles at the insertion points. Yeah. So holomorphic functions at most finite order at insertion points. Finite order poles. So the global version of our Lie algebra in this simplified example is simply to take Lie algebra valued functions, so SL2 valued functions, which have the same dependence, holomorphic dependence. So now, what can you do? Pick around each point, pick a local coordinate. If I'm given some element here, which is a Lie algebra generator, say take tensor the function, I can take the function and expand it in this local coordinate. This is the local coordinate psi I, and since this local coordinate has at most finite order poles, it is of the form some numerical coefficients, local coordinate to the nth power, and finite order pole means it doesn't go all the way down to minus infinity to an essential singularity. Now, if you have these coefficients, it's straightforward to get a Lie algebra element. Well, the Lie algebra element in our affine Lie algebra will be AIN, and now I'm replacing this by the corresponding mode. And I have here a sum which starts at some finite value, maybe negative, but this acts on the type of modules we consider in a consistent way by finite sums. So no dangerous infinities. So now what we do is we do this at all insertion points, and we only act on one of these entries. So here is my ANI, JNI, and the other ones I take simply identities, and I'm summing here over all insertion points. So this looks like a co-product, in very roughly speaking. Yeah. So and this acts. This acts on the space I was defining here, H lambda. Okay. H vec lambda. And you see, it depends on the choice of complex structure, because what's holomorphic depends on the choice of complex structure, and F had to be holomorphic. Well, I say it acts, so if you check that this Lie algebra acts, you have to do one nice calculation. The affine Lie algebra had a central extension. This here doesn't have a central extension. This is not cheating. But the central extension in the affine Lie algebra can be written as residues. And you know that the sum of residues of such a function vanishes. This is something you have to do if you check that this action is a consistent action. And now, well, we want to look at very specific elements in the algebraic dual. And this we can do. We want to impose invariance under the symmetries of the CFT, which we have encoded here in this toy example in Lie algebra valued functions. So what you do is you take a vector space which is H lambda, and then you take the algebraic dual. Well, if a Lie algebra acts on a vector space, it also acts on the algebraic dual, and now you take the invariant vectors. So these are the vectors that are annihilated by the Lie algebra. This is imposing chiral Ward identities. So this space of invariance, this is what is called the conformal blocks. So this would be the conformal blocks for the curve X and P. And this is a definition which almost literally appears in important mathematical work. So if you want, for example, to see Falting's proofs of the Verlinde formula, he will use this definition of conformal blocks. And there are good reasons to do this, right? Algebraic geometers have been interested in this because these spaces appear as spaces of sections over moduli spaces of bundles on curves. And that's what they wanted to compute. Okay, so we got some nice spaces. Actually, it's not so hard to check that they are finite dimensional. If you work with integrable highest weight modules or even with highest weight modules, well, they're not one-dimensional. So we cannot say we found correlators. And I mean, even if it would be one-dimensional, a correlator is a single distinguished function. And we've defined a vector space. And this is natural because in the end, what I did is I took chiral Ward identities and I described solution spaces of linear systems of systems of linear differential equations, and that's a vector space. But we are looking for a concrete correlator. So we will need tools to talk about explicit elements in these these vector spaces, and these will be our correlators. And here the problem of constructing correlators splits. It has a problem which I have described here in a very algebraic way. You could do it in a more complex analysis fashion. Yeah, so finding the spaces of conformal blocks and then finding solutions inside. And if you are familiar with the classification of characters of reductive Lie groups, this was something which made a lot of publicity in the press about 15 years ago. The title in the New York Times was a formula as big as Manhattan, which is a very scientific title for a math paper, right? Well, anyhow, there's a similar thing. You solve Harish-Chandra equations, and then there's a combinatorial problem on top of this to identify specific elements which are characters. And we want to get a grasp on these spaces, which is so tight that we can select individual elements here which serve as correlators. And this problem is solved. And in this sense, I would claim that two-dimensional CFTs are among the best understood quantum field theories. So let's, still before I continue here, let me make a couple of comments. So I talked about algebraic geometers. They call these spaces of non-abelian theta functions. That's maybe one thing. You can identify these spaces also with state spaces, and Chern-Simons theory assigns to surfaces. This is something I'm not able to cover here, but in principle, which makes the relation to TFT at the level of theories with actions and in a classical formulation. But let me do one little exercise. So who has heard the notion of an Ishibashi state? So about 20 years ago, everybody knew what an Ishibashi state is, because that was the time when people were interested in D-branes. And if you want to, D-branes are boundary conditions for two-dimensional CFTs. So you want to construct one-point correlators on the disk, and people were looking at writing boundary states, and they were linear combinations of Ishibashi states. Well, an Ishibashi state is actually nothing than the conformal block for CP1, so the Riemann sphere. Let's choose a quasi-global coordinate, so infinity is the only point missing. So we have two insertions at 0 and infinity. How do our blocks look like? Well, I have to choose here a local coordinate. Well, I'm choosing the local coordinate z. Here I'm choosing as the local coordinate psi infinity 1 over z. Now you are expanding. Well, what are the functions that have at most finite order poles at 0 and infinity? Well, these are functions of this type where n can be a positive or negative integer. And now you take such a thing and you expand it, and then the corresponding expression here becomes JAN. If I take now here JA tensor Zn as the Lie algebra object, tensor 1 plus 1 tensor JA. Expanding here in minus z gives me minus z to the n. And what people called Ishibashi states was simply the solution if you take now h lambda tensor h lambda prime of those states that are invariant. Well, you can show that they were saying these are formally using scalar products that maybe literally do not exist. They were saying these are states that are annihilated by this combination of operators, and in the case of a free boson, people were writing this down as a generalization of a coherent state. So this is an alternative point of view on conformal blocks, that you have something that's kind of a generalized coherent state. Well, now at this point, I make 10 more minutes. I will continue for 10 more minutes and then I make the break. Is this okay? Yeah. But if I forget to make the break and you're not reminding me, it will be your fault. Yeah. It's always good to have somebody who's guilty. All right. Okay, good. Now, what you should see here is that I fixed a complex curve x. I pointed out that the complex structure of a complex curve is not unique. Now you start to vary the complex structure on x. And then these subspaces, which are invariant under this action, they will change. So what you are getting is you will get a finite dimensional subspace over each point in the moduli space of m points on a curve of genus G. Now, maybe your intuition tells you that these subspaces which depend on P, they fit together into a vector bundle. Well, it's almost true, but you have to work and you have to say something about the vertex algebra, and it's a theorem, a relatively recent theorem, if the vertex algebra is C2 cofinite. So there goes some work into it. So what we get by combining these subspaces is a vector bundle over this. It's actually a bit more. There is some famous gadget which is called Knizhnik-Samolotchikov connection. You can endow this vector bundle with a connection, so a covariant derivative. This connection is actually almost flat, projectively flat. Read flat if you don't know what projectively flat means. So what we have here is a vector bundle with connection over a space. And if you want to imagine this space, remember what we got in the case of a complex curve of genus 1. Well, this was this fundamental domain. So already in this case, this was a non-trivial space. In particular, this space has a fundamental group which was, just by geometric results, the mapping class group of the topological surface of genus G and M points. So what do we have here? We have a flat bundle over a space whose fundamental group we know. Now, what do we need to recall this bundle up to isomorphism? Well, you need holonomies. You choose a base point, and then you go around in your bundle, you look what parallel transport does, you're back to the fiber, and parallel transport will be non-trivial, but it will obey the group law of the fundamental group. So what we are getting here from all this story is representations of the mapping class group. Yeah, so this is the upshot of a long discussion now that the conformal blocks form non-trivial, in general, representations of the mapping class group, and here I should say conformal blocks for a surface of genus G and M, and it's the mapping class group of sigma G and M. And there is a famous type of theorem that Riemann-Hilbert correspondence is that if you are only interested in the iso class of bundles, it's exactly this representation of the fundamental group that you should record. What is important about this representation? Well, I told you that there is a connection, so we can look at flat sections, right? Constant section. If I take such a section and I transport it around, it will come back as something different. So these local sections are typically multi-valued functions. So you see that we have a problem for correlators which should be functions of the shape of the curve and not multi-valued. But what we see here is that this problem of finding single-valued function has become something algebraic. Namely, it means that we have to find here sections which are invariant under the action of the mapping class group. Okay? So, for correlators, find sections that are invariant under the mapping class group map sigma GM. Well, this is one constraint that we will have to solve. In order to solve it, this description of conformal blocks will be inconvenient. So what we will do is, what is essential here are the holonomies of these multi-valued sections. And you can store the same data in a different mathematical gadget, and that's called a modular functor. So we will take this, define a modular functor, and then solve this problem of finding invariance in using this modular functor. And that's the goal for the third lecture. Let me announce what I have to do after the short break, because this was the signal for the break, right? There's one more requirement I have to add. I was mentioning that complex curves can degenerate, and we have to control what's going on under degeneration. This is something which is not strange for a field theorist. These are called factorization constraints. So you've seen this in other contexts in terms of cluster expansions, that if you pull things apart, that there should be a controlled behavior relating this to some other geometry. That's what I'm formulating. This will be also captured by the modular functor, and then I will explain how you get the modular functor, and we will solve this problem in terms of modular functors. Good, let me make the break. Oh, okay, so I have 2 more steps to take. So what I tried to convince you is that all this construction gives us, in the end, some representation of mapping class groups, but this is not really correct to say it this way. We get for any genus and any number of marked points, we get a representation of the corresponding mapping class groups. And even we have to choose these labels, these representation theoretic labels, which are representations of the VOA. So this is a huge system of representations of the mapping class group. Another thing we have is such a complex curve can degenerate. And let me try to make a hopefully intuitive picture. So there can appear something which is called an ordinary double point. And there is a way to resolve such an ordinary double point. In principle, this is standard algebraic geometry. So what you do is, here are 2 lines. I'm doing a real picture here. Here are two lines running into each other under different directions. So you can blow up this point, which roughly means that you are replacing the point by its space of directions. Then these things are running into the point from different directions, and it will be systematically resolved into the situation where everything is the same, except for that the point has been doubled, and that the curve is now again a smooth curve. Now, with a considerable amount of work, you can show that it is still possible to define conformal blocks here on this curve that is degenerate. So put differently, this vector bundle can be extended to degenerate curves. And now here I could also define conformal blocks, and I would take the same labels at points lambda, which are far outside. I have here lambda 1, which is a representation of our vertex algebra V, which sits at a point P1. So that's, of course, unchanged. But here I have 2 more points, P plus and P minus. So plus is not better than minus, yeah? So it's just 2 points. So what you need to do here for this curve after blow up is you have to choose 2 more labels. What are the labels you choose? You're choosing any simple representation, and here the conjugate one, so the dual one. And you do a direct sum over the duals, and then the claim is that there is an isomorphism. I'm cheating here at this point because this formula makes sense and is proven if the category VREP has finitely many simples and is semi-simple, so any object is a direct sum of simple objects, yeah? Is finitely semi-simple. I think several people here in the audience have already a conjecture what one should put here in the general case. There should be a coend. And people in the vertex algebra community are working on this problem to extend this. So what you see is that these spaces of conformal blocks, they are very closely related, even if I let this point degenerate. So for example, if I'm starting with a torus and 3 points, and I'm squeezing the torus, I can relate this to the sphere and here I have my old 3 points, and here my additional points mu, mu bar. So this is a very tightly constrained system. In the finitely semi-simple case, this restrains in particular the dimensions of the conformal blocks, and this goes under the name Verlinde formula, and I've written down some information on the Verlinde formula for you, but it's not the main focus of this lecture. So what do we end up? We have to somehow organize a lot of algebraic information. We have to organize for every genus any number of insertion points, any choice of labels. We have to organize a vector space that carries a representation of the mapping class group, and we have to keep track of these maps. And there is a dedicated gadget for this. And this is a so-called modular functor. So let me write down what a modular functor is and then walk you through the definition. So I need a geometric side and I need some algebraic side. What is my geometric side? Well, I have here zero-dimensional structures which are points. Zero-dimensional is somewhat of a cheat because we had to choose local coordinates. You cannot really quite completely get rid of the local coordinates. I didn't discuss this. So it is much better to say that the local coordinates specify small disks around these insertion points. Yeah? And if you look into Touraev's book, for example, he will go a bit further and he will observe that you can get rid of many aspects of the disk, and essentially you should have just to keep track where the x-axis is going in this disk. And he will work with a structure where you have little ribbons going through this point. Think about this as the infinitesimal remainder of an x-axis, and this is appropriate. For us, this will be now for the moment circles, so one manifold. Here we are assigning to each of these circles, we are assigning an object which is in the category of representations. We are assigning some representation. So to a closed oriented one manifold, and yeah, it should be compact, so it's a disjoint union of circles. We assign here, well, the thing where this lives, we assign a category. So for example, if this is S1, the circle, and n copies of this, we will assign vrep and n copies of this, but I have explained to you earlier on that there is a natural tensor product of such categories. So this here is the ground floor of the structure I'm defining. Now, here I have the second floor, two manifolds. Well, the two manifolds, I'm drawing them in a way which you've maybe seen in some topology course as an oriented surface with ingoing and outgoing boundaries. Now you are going to say, oh, you didn't show us any outgoing boundary. There were just boundaries before. They're just disks over there. Well, this is the reason why I wrote here prof. Actually, I will work technically without showing this to you later with pro-functors and not with functors. And then this distinction between ingoing and outgoing becomes less important and is under control. But for the moment, think about this, that you can take such a boundary and declare it to be ingoing if you assign instead the dual representation. That's not misleading. So here we have surfaces with boundary, and here we assign to this a vector space. This is the second layer. And the third layer, well, we have still one important player to take care of here. The third layer will be mapping class group. So on each of these things, I have the mapping class group. This is a geometric gadget, MGM, and it will act on the vector spaces, so we will assign to this linear maps. So this is a three-layered structure. This is a familiar structure. It's called a bicategory. And now we have to look into this. We have already used that this is a category. In a category, you can compose morphisms. That's the essential thing. So in a bicategory, we should be able to compose one morphisms. This is called a one morphism, and this here will be called a two morphism. Well, how do you compose such a thing? This is a one morphism from 3 circles to 2 circles. So you will be able to compose this with a one morphism to, say, 4 circles, yeah, by gluing this together. Yeah. So this gluing together takes care of these isomorphisms. Indeed, I was mentioning that in general, this will be a co-end, and pro-functors, just for those who have been exposed to more, the composition of pro-functors is also defined in terms of co-ends. So this is a very natural thing. So you see that what we do is we take the information that we need, namely, what are the vector spaces? What is the action of the vector spaces and how do they factorize? And we are plugging them into a new structure which is called a modular functor. So if I would have to write this down in an explicit definition, I would explain that this here is a bicategory, this here is a bicategory, and that there is a functor between them. Actually, it's a bit more than a bicategory. It has its own tensor product because you can take unions of circles and unions of surfaces. So in any case, a modular functor is a functor here. And this is the algebraic gadget that will keep track of all this data. Now comes a point where we have to be very careful. VREP, as I explained, it is a category which has a lot of structure. Remember, this is under our Ribbentrop-Quartier category with non-degenerate braiding. So it is actually what's called a modular tensor category, not necessarily semi-simple. So it has all this structure. You can study conformal blocks and try to extract this modular functor from it. This is not completely done. You can instead take this category as an abstract category and directly construct a modular functor. This is done. The fact that the two constructions give equivalent results is plausible, but not proven. And it is our working hypothesis. But if we do this, we have here captured the information we need to find correlators. Because what do we need to do? We need to find here elements in these vector spaces, which are invariant under the mapping class group, and moreover, well, what we have is that under gluing these vector spaces are related, and the correlator for X is a specific element in here, and it should be invariant. It should agree with the components, component-wise with the correlators here. So this is the problem, and it's a highly constrained problem, and it has solutions. So what is the thing I should do now? I can move, no, let me do this on this blackboard. I can move to full CFT finally. So, so the first thing is we encode the underlying chiral CFT in a modular functor. And maybe before I continue, just a word here. There are modular functors which can be extended to something that's bigger than this board. And let me write this board systematically 1, 2, and 2 plus epsilon. What is this 2 plus epsilon? I'm allowing as two morphisms only mapping class group elements. You could imagine a situation where the two morphisms are 3 manifolds. Well, here the 2 manifolds are already 2 manifolds with boundaries, so these are 3 manifolds with corners. And what is a 3 manifold with corner? Well, first, a 2 manifold with boundary is, for example, this one. Yeah, so maybe you want to draw it in this way, but this is really the same. Now, a 3 manifold with corners, it looks like a tin you can buy in a supermarket. Yeah, and then you see already the outer circle, it is related by a tube, and similarly there will be tubes relating the inner circles. Now, what you see is this looks already like a braiding. Yeah? So, and in fact, if you have, if you can extend the modular functor to all 3 manifolds with corners, and I should have said oriented 3 manifolds with corners and several qualifiers, then we have a so-called once extended TFT, 3-dimensional TFT. Yeah? So it is for sure that if the underlying category C is finitely semi-simple, that such a modular functor can be extended. Let's be careful about the converse and not discuss it here in this situation. If you are working with cobordisms as you should define them, there are no go theorems that you cannot do it for non-semi-simple things, but you know no-go theorems are made to be evaded by relaxing some of the assumptions. Yeah? But I think then you shouldn't call it TFT anymore. Okay, now what is the plan for the next lectures? So what we will do is, if I take C V rep, I will construct. There is in fact such a construction of a three-dimensional TFT based on C, and this is the Reshetikhin Toraev construction. This is something you can in principle take from the shelf since the mid-90s. There it's not called a once extended TFT and it's written up in a different way, but that's what it is. This works only if C is semi-simple, so no logarithmic CFTs. And I will show you how to obtain correlators in this framework. That's the first construction. Now, the second construction is if we use the fact C with reversed braiding is isomorphic to the Trinfeld center, then braided equivalent to the Trinfeld center, well, then, which is our non-degeneracy of the braiding, then I can look at the construction of a modular functor based on a Trinfeld double. There are various ways to construct it. So if C would be H mod, then we could use the Kitaev construction, but this is pointless for our purpose because C is of the form H mod if and only if there is a faithfully exact monoidal functor to vect. And typically this doesn't exist because here the so-called quantum dimensions are non-integers. Yeah? So we cannot really use the Kitaev construction, but morally we are in a world of the Kitaev construction, and what I'm going to use here is a skein theoretic construction, which is the called the stringnet construction. And then we can construct in this framework at least the bulk correlators. In fact, maybe I have time to show you a bit more how to construct boundary correlators in this framework as well. Yeah? So two different constructions. This construction is from 2000 to 2005. This here is last year. Yeah, so this is insight we didn't have available. This here is much easier because you're only doing two-dimensional geometry and it avoids semi-simplicity. So this is the important progress, and we hope to extend this to larger classes of categories. Well, okay. So now, what is the problem we want to solve? We have one of these functors, and we want to describe what is a consistent system of correlators. So the correlators should be elements in the spaces of conformal blocks. Yeah. So we need to find a way in this framework to address individual elements in spaces of conformal blocks. But let me first say what we want to: consistent systems of correlators. What is the thing we want to find? So we have an assignment which assigns to every surface, and I will have to be a bit more precise about the structure in a moment. It assigns a vector space here, and we want to find here a specific element, correlator C of S. Well, this surface here, we're now talking about full CFT. This surface has actually quite a bit of structure. So, of course, it has field insertions, and we have to discuss what this means. But we will consider the case where there can be also defect lines, topological defects joining this field insertion, and they can be arbitrarily complicated, so this could come back and go here. So we've really to specify a lot of data. We take this, we take here the underlying topological surface, we take the conformal blocks, and the vector we find has to depend on these decoration data. And it has to be defined in such a way that first requirement, invariant under the action of the mapping class group. Map. And it has to be compatible with sewing or factorization. Well, actually, if you think, this here takes into account that we have really single-valued functions and not multi-valued sections. You have to be very careful what you mean by the mapping class group, because now we have additional decoration on the data. And this decoration on the data, well, let's take the naive definition that this should be kept fixed under the action of the mapping class group. Now you realize this is a very bad definition. But why is it bad? Because these are topological defects. So this is like in an Ising model changing along a line ferromagnetic coupling to antiferromagnetic coupling. You cannot observe this line. So if I ask that this line is preserved, but you choose a different line, why do I keep this line pointwise fixed? So in the end, this is a question which leads to a lot of additional structural insight. This will be the last point of these lectures. But for the moment, let's take the naive. Definition. Okay, so in any case, we have now transformed a problem which contained a lot of mathematics into a problem which becomes more and more algebraic. And we will be able to solve it soon. So now we have to discuss such a worldsheet, and my worldsheet is not very appropriate. So I have to discuss this decoration data, and let me take the data I have also here in the lecture notes. Let's discuss things on a disk. Let's assume that there is a defect line running here, and then we have a field insertion. There is a bulk field. There is a field living on the defect, and there is a boundary field. And now we assume that the correlators have all the symmetries that are encoded in a certain vertex algebra. So in the background, we have C, VREP. We are not interested anymore in the fact that this is VREP. We've just a category which has a nice structure. Now we have to start to decorate this. Well, the first thing is what do we assign to surfaces? Well, if you're interested in theories that are based, West-Zumino-Witten theories that are based on SL2, then it happens, they depend on a parameter, the level, a coupling constant. For a level that's 0 mod 2, you can find two different theories. Well, if you look at Peter Bauknecht's talk, he will introduce gerbs. You can write down Lagrangians in terms of gerbs, and there will be two different theories that can be constructed in terms of a gerb on SU2 and a gerb on SO3. in any case, I need some additional label. It is a point of a long analysis that this here should be labeled by a special symmetric Frobenius algebra. So each two-dimensional patch will be labeled by a special symmetric Frobenius algebra. Let me explain what a Frobenius algebra is. So, because some of you will be familiar with the notion of a Frobenius algebra, some not. So let me first say that a Frobenius algebra is an additional structure on an associative algebra. So let A be an associative algebra. Well, could be in vector spaces, but the essential thing is I can formulate it in any monoidal category, because then I have an object, I can form a tensor product of the object with itself. I can consider a multiplication, and multiplication is associative if these two morphisms are equal, and I think this should be self-explanatory. Now, for a Frobenius algebra, I require that A is also a co-algebra. What is a co-algebra? It has a co-multiplication. And it has, well, here I also have a unit. What is a unit? Well, it is an element in A, so it is a morphism that goes from the ground field to A. And we have here a co-unit which goes from A to 1. This is called epsilon, this is called delta, and the pictures are just upside down the same. Well, this co-algebra is also a co-algebra, and this algebra structure have to be compatible. Maybe you've seen this in the context of Hopf algebras, but here we are asking for Hopf algebras, you will ask that the co-product is a morphism of algebras. But we are asking here for something else. We ask that this is a morphism of bimodules. Well, what is A is a bimodule over itself, and A tensor A is also a bimodule over itself, where I'm acting here from the left and here from the right. What does it mean? Well, it means that first acting and then co-multiplying is the same as first co-multiplying and then acting. This is the compatibility with the left action, and for the right action it is first acting and then co-multiplying is the same as co-multiplying and then acting, and if you look closely these two diagrams are the same. This is a Frobenius algebra, and it is and let's assume that this here is rigid. It's a nice exercise to show that this implies that A and A dual are isomorphic. This is the more classical definition of a Frobenius algebra. And, here I had a few more qualifiers. Symmetric. Well, why are they isomorphic? Well, I can take here a product and here the co-unit. Then I have here a morphism from A, and here this is A dual, this goes left, so this is a right dual. And I can equally well do this. Now you see, this looks pretty much the same, sorry. Yeah, so let's do it in this way. So this is a left dual. We are in a pivotal setting where these two are the same. So it makes sense to ask that this is the same. This is the condition that it is a symmetric Frobenius algebra. And concerning special, well, special means that this here is a one-sided inverse of multiplication, which means that multiplying and then doing this gives you the identity, and there is some more condition. Well, the fact that it's a good idea to label these two-dimensional patches by Frobenius algebras is something I'm claiming here. It will be justified in the end by the fact that then I can construct a consistent set of correlators. There is kind of a converse result which shows that you really have to impose this. This is the last paper in this a series of papers we were writing some long time ago. So paper 5 in the short. And so Vincentas knows the terminology. Okay, so here I have two Frobenius algebras, here A and B. And if I say Frobenius algebras, I will usually mean special symmetric Frobenius algebras. Now, I need a label for this defect. Well, what should be a good label here? Well, I will label the defect lines by bimodules. Yeah? And AB bimodules, the defects are oriented, so I don't have to explain you in which way this is an A and a B bimodule. Then, so I have here, let me stay in the same notation as I have two bimodules X and Y. What do I do with boundary conditions? Well, for boundary conditions, I have here one adjacent face. I will label this by an A module. And here, such a boundary insertion can change the boundary module. And here it has to be an A module, and here it has to be a B module. So this is a very natural labeling. So now I have to label the field insertions, which I have here. And this is a trickier thing. And it will be ultimately justified again by the fact that I will be able to successfully construct correlators. So now, when should I stop, Paolo?
10 minutes.
Fine, yeah, then I can adjust it a bit too. I want to have the labeling for tomorrow. Good, so, well, if I'm talking about a boundary point, let's go back to the very beginning of this lecture. The double of this disk will be a sphere, and the boundary points will have a single pre-image. So, on the double sigma head, I can do chiral CFT, because this is a complex curve. So, you see, it's very natural to ask for a single chiral label for boundary fields, but for bulk fields, which have two pre-images, I will have two chiral labels. That's the combination of left movers and right movers. So you see that here, for this insertion here, I will have to find something that depends on M prime, and I should choose one chiral label I in V rep. So here A is an algebra. I can consider the category of representations of A modules internal in C. These are, by our orientation conventions, these are right modules. If I take a right module and I tensor it to the left with some degeneracy space, this doesn't harm the right action. This here is also right action. It turns out that the right label for a boundary field which has chiral label I is this, but by taking on top of this an element in this vector space here that's defined in a completely algebraic way. And of course, all kinds of challenges appear at this point and they are solved. So for example, you know that the dimensions of these vector spaces have to obey certain consistency conditions. They have to form non-negative integer representations of the fusion rules, and it's shown that this holds. Yeah? What I should also explain to you is what's going to happen with a bulk field here. Or let's do it here right away for a boundary field. So we have here a module which is something which is a left A and a right B module, and Y is also a left A and a right B module. Okay, so it's quite natural to look at A-B bimodules. Well, here we have now two chiral labels, J and K, to take. Well, the idea is again to incorporate them by tensoring. But now you say, okay, that's bad, because I have destroyed here the left action by tensoring from the left and the right action of B by tensoring from the right. It's not so bad in the end because, well, I have an action of A and of B on my X, but if we are working in a braided setting, so if I'm tensoring here with some J from the left, and I'm using the braiding, I still have a module structure here. And for some reason, which has to become clear tomorrow, I'm using for K the other braiding. And this is what I'm denoting by putting plus and minus signs here. So obviously, nobody gets up in the morning and writes down this bimodule structure. Yeah? But you'll see why it's very natural to write them down in this way. So a bulk field, well, here I can always draw a bimodule for free because I can take A as a bimodule. So a bulk field will be simply Hom A, J, tensor X, tensor K, so A, tensor K, A, and we take this specific bimodule. If you take the dimensions of this, these are vector spaces, so these are ordinary dimensions, then a very nice thing happens. These integers commute with the action of the modular group. This can be proved. This needs a bit more machine than I'm able to develop in these lectures. So you'll see in particular, we will construct modular invariants. And this was actually historically the starting point. There was a program which was quite influential in the late 80s and in the 90s that people started to classify modular invariant. They found ADE patterns, they were quite happy, and they thought, okay, maybe this is a way to classify CFTs. But then we found in my PhD thesis matrices that commute with the action of the modular group, but that cannot correspond to any physical CFT. So the classification of modular invariants was dead. And it took us about 5 years of real desperation to come up with this notion of special symmetric Frobenius algebra. And this does the job, and I will explain to you tomorrow why it does the job. And maybe a last word for the young researchers here. When we found the solution, we wrote a paper as you are doing it. We submitted the paper, and the paper was rejected with a very brief report. There's nothing new in the paper. So if your papers are rejected, well, keep on going. And for the older ones here, our papers are also sometimes rejected. It's something the community doesn't really speak about, but don't be discouraged by such things. If you think there's something new in it, go on. There's a high chance that other people than you will be wrong. I think that's a point to close the lecture.
When you speak of this tensor product from the left and from the right, it's automatically associative?
Well, the tensor product is in C, so it comes with an associator.
But that one comes with the opposite way.
Oh no, here we do not discuss associativity. The important thing is that we obtain just some new bimodule. Yeah, so that's the important thing. And maybe one quick comment. An algebra in a monoidal category, this is something you've seen in John Barrett's talks. Yeah? Because he was considering algebras with symmetries. What does it mean? He had a category which was something like G-rep, and then he had an algebra which was transforming under this, and then he had a multiplication that was compatible with this action. So really, you see what we are doing here is something which is quite in the same spirit. So we have really an algebra that is compatible with symmetries. For Hopf algebraic people, this would be a way to realize this would be to use module algebras over a Hopf algebra. We cannot use it because our categories typically do not have fiber functors. But morally, we are using here a setting where you have symmetries given by the CFTs, and you're considering algebras in it to get something like spaces. So there would be an alternative view on this as kind of a non-commutative geometry. Maybe that was a comment for the chairman.
Okay, so let's thank again the speaker. And